Okay, welcome everyone to the very last session of the symposium. Thank you for staying that long, and but don't be afraid, it will be nice. First, it will be a bit different because we will get a session in two parts. The first part is what you had before, so 2 presentations, and then there will be the results of the PETRIC 2 challenge, which is the PET Rapid Image Reconstruction Challenge that Edo is going to cover. The first presenter is Julián Tachella. He is based in Lyon, right? CNRS research scientist, and he's one of the co-founders of Blur Lab, and one of the developers of the Deep Inverse library.
Perfect. Does it work? Yes.
Yes.
So thank you very much for the introduction. I know we are in the end of these 2 days, and I'm gonna be speaking quite math and methodological. So I hope the coffee just now it's kicking in and keeping you awake. So I'm gonna be speaking about a work we've done very recently. It was led by my PhD students Jeremy and Victor, and we're gonna be presenting it in iClear this year, which is about learning from incomplete data. So let's start. So I'm gonna speak about what we've seen these 2 days, is inverse problems. Just to make sure we are all in the same page, the famous equation of the inverse problem, we have x that it's some unknown volume, image, or signal. We have a that it's a forward operator. Here I'm going to assume that it's a linear forward operator like we saw in PET, SPECT, and so on, or tomography. We have y that are the actual observed measurements, and we have some noise that I'm going to write Gaussian here, but it could be Poisson, it could be other things. So the 2 examples I'm going to be considering, but among others, are accelerated MRI, where A is measuring a subset of some Fourier information, and imaging painting, where we are missing some pixels. I'm actually not sure if I should go in the middle. Yeah. I guess it's better, yeah. All right. And imaging painting, which is kind of a toy problem, but it helps us visualize and understand the mathematical concepts I'll be speaking about. Okay. So right, we want to solve this problem, and we've seen that there's many different methods out there for solving it, but I would argue that most of them fall into this category here, or many of them. The ones that are used learning, where we train a reconstruction network, okay, with a supervised data set of pairs of measurements and expected ground truth signals, okay. And so here f of theta is something that it's a generic neural network, but if you look at the definition I wrote down there, it depends on the measurement and it depends on the operator. So it can be your favorite TV reconstruction with a lambda parameter that is unknown, but be careful because it will be AI. Okay. So it can be an unrolled network, it can be whatever you want. All right. So this method actually works very well, and we have seen that it kind of took the whole field in a few years, where the best performing methods follow this kind of approach. But there's a problem. And the problem is that when we go to medical or scientific imaging, having these ground truths to train our model on is not very easy. If you think about reconstructing a black hole, we don't have a nice ground truth data set of black holes. The same for medical imaging. Okay, we have some pictures of brains, but they're always limited by the device we're using to generate these images. We don't really have the perfect ground truth that we would like. Okay, so how can we do to still use AI or machine learning to train these reconstruction models without having access to ground truth? And this is a problem we've been working for many years now, and so the setup is the following. We assume we have a data set of measurements, so we have, for example, a PET machine, and it's giving us, we pass different patients through the machine, and it's giving us measurements. And now we just have these measurements, and we want to learn the reconstruction function from the measurements. But we assume we have multiple patients, okay? So it's a data set of measurements. So what can we do? The most naive thing we can ever try is say, okay, we're gonna maximize the likelihood, or so try to make the network to be measurement consistent. So we're gonna basically take our measurement here, we're gonna pass it through the network. It's gonna give us something. We're gonna compute the associated clean measurement in the measurement space and compute the loss between the two of them. This is kind of similar to what when we do maximum likelihood and reconstruct a single signal. But what's the problem here? I don't know if you are an expert in flamingos, but that's not a flamingo. It's kind of a mixture of a duck and a flamingo. So, and actually the neural network is not realizing that it's not a flamingo because it's only computing the error in the observed pixels, right? And so there's no signal coming back and telling the neural network there's an error there. So this naive approach of just trying to enforce measurement consistency is never going to work. When is not going to work? When we have an operator that has a null space, when it's an operator that is incomplete, that is losing some information. And so we are a bit stuck, but we still want to learn. What can we do? So the first approach is to say, in many applications, we might have multiple operators. The operators might vary from acquisition to acquisition. If we think about in painting, maybe we're taking photos of flamingos, and from one flamingo to the other, the mask changed place. So in that case, we can see that the missing information in the first picture is not the same as the missing information in the second one. So if we never saw the I don't know, the eyes of the flamingo, we're seeing it in this picture. So we kind of can generalize, and we have different bits of missing information. So in MRI, we can imagine that the acceleration masks we are using are changing from patient to patient. So this is giving us different frequency information from patient to patient. Okay, so in this case, again, doing measurement consistency is not a solution. Okay, why? Because if we assume no noise, to simplify things, as a neural network that is just applying a pseudo-inverse to the measurements is perfectly measurement consistent, and it's not great because we wanted the neural network not to do the pseudo-inverse, otherwise we will not do a neural network. So what can we do? And one solution is based on splitting. So it's an idea that's very close to what we are used to, which is cross-validation and so on. And the idea is the following. We'll take some measurements, and to avoid learning this pseudo-inverse, which is just the identity here in the painting problem, we'll split the measurements into two, feed one part of the measurements to the neural network, and ask it to predict, well, here, everything. So the splitting loss will look something like this, where for every sample, we will randomly split, and then pass just one part to the neural network, mask the other, and ask to predict everything. And for example, in the first flamingo, we might have this mask, but then we will have another flamingo. Well, it should change the flamingo, where we split differently, and we are always splitting randomly. Okay. And why is this a good idea? Well, first we see that we cannot learn the identity. The kind of the generate solution is not a solution anymore. Why? Because we are asking to predict something that the neural network hasn't seen, so it needs to do something more than the pseudo-inverse. Okay, and we can go further and analyze this mathematically, and we can see that actually the solution can, in expectation, so if you have a sufficiently large data set of measurements, is this formula here, which looks a bit scary, but it's quite easy to understand. The first term is the oracle, is the MMSE estimator, so the best estimation you can have of the signal given the split measurements. And the second one is something in the null space of the operator, so in the part where the operator is missing information. And these two terms are controlled by this matrix here, which is given by this expectation. And the expectation is just measuring what is the variety of operators I have. So I'll give some visual example in a second. But if this operator, if this matrix here, Q, is invertible, then the null space term is 0, and we just get the MMSE estimator, and we're happy. We are learning exactly the same as in a supervised case without any supervision. So let's have an example where this is the case. So we keep in painting because it's easy to visualize, but this extends to PET, SPECT, and so on. We take our mask for a given sample. Let's say that we observe the pixels in the second part of the image, and we say A1 will be, so the first, the thing we put into the network is the middle, and A2 is the target. Sorry, A1 and A2 is the target. And then we have another operator that is different. And now we keep the same A1, but A2 changes because the mask is changing from sample to sample. And we see that taking these two together, this one is giving me the estimation of this bit given this one, and this one is giving me the estimation of this bit given the other. So when I put everything together, I get an MMSE estimator. All right. So as long as I can cover the whole space, and this is the expectation we have here in our condition, as whole as this expectation is covering the whole space, we have what we want, which is the Oracle MMSE estimator. Right. But the talk today was not about multiple operators. I'm making my life harder, and I just have a single operator. Why? Because in many applications, for example, my MRI scanner is not changing the acceleration mask from patient to patient. My camera has the same broken pixels each time. My CT angles are always the same, so I don't have multiple operators. What can I do? I'm stuck. I have a null space, a missing information of the operator, which is always the same. Okay, but there's a trick, and there's a trick we've been doing for a while now, which is assuming that the distribution of the images I'm imaging are invariant to a group of transformations. What does it mean? So if you think about a picture of a brain, for example, if we rotate it, it's still a brain. It's still in distribution in a way. Okay, you could argue that there's no scanner that will take this picture, but there's small angles and small rotations that always will appear. We have been hearing about motion for many talks here. So there are these different rotations that are inherent to the distribution. And so we can assume that the distribution is invariant to a group of transformations, which is an assumption that it happens a lot in machine learning. Why this is useful? The trick is very, very simple. We take our inverse problem equation and we insert a transformation and its inverse. So if you think of any transformation, they're typically invertible, except for maybe border effects, but let's forget about them for a second. And so we see that looking at this equation, which is the same one as the original one, but it has a different interpretation. The interpretation is that now I'm seeing a different image, x prime, and a rotated image through a rotated operator. Okay, and why is this important? Because now I have multiple operators. So now I have a family of operators, which are my original operator concatenated with the transformations inherent in my dataset. So implicitly, I've done some, just by imposing prior information about my distribution, now I'm having a family of operators, and now I can do something very similar to the splitting, but now the family, so the sets of matrices that I have are all related by transformations, and I'm going to take the expectation over all possible transformations. And this is what we're proposing here, is the equivariant splitting loss, which averages over transformations. Okay. So when does this work? So the answer is the same as before, but now adding t's instead of generic a's. Okay. So we look again at this thing, and what we need to understand if this matrix QA1 is invertible or not. And again, we can take the example of inpainting, which is very simple, and we can think now that my transformations are shifts. So for example, horizontal shifts, right? Vertical shifts, sorry. So if I shift my mask, I'm going to get another mask where I get exactly what I had before, which was a sufficient overlap between both of them and a common A1 and A2 that covers the rest of the space. So this is a very simplified example with two operators, but you can imagine that as you have more transformations and you cover more of the space. So again, when you compute this expectation, you can see that you are covering the whole space, that you have masks that are going all over the place. So you don't have a null space in the end. So now we need to compute this loss, okay? And the issue is that if we go back, we have this expectation here. So we need to average over all transformations. And you might ask, okay, how do we do this in practice? There's two ways. First one, you just do Monte Carlo. So as you would do kind of in augmentations, you just randomly sample a transformation per batch, per mini batch in your training, and then on expectation you're gonna be minimizing that loss. So that's one option. But there's even a more elegant option.
Time's up. Go ahead.
Please move forward.
Yes.
Very dramatic.
Yes, I'm gonna speed up. So you can use an equivariant a network. So I'm gonna skip to the results because I thought there were 30 minutes, but I got it wrong. Are you sure it's?
It is 30 minutes, right?
The standard invited duration has been 30 minutes.
Yeah.
Okay.
But I don't know what else you've got planned for the second.
Go ahead.
No, you're right.
So we had an unexpected.
Sorry.
No, you have 25 minutes for yours.
Great, so I can actually speak about.
An incompetent chairman.
I was not checking.
All right. So going back to the plots, we said there's one solution which is doing random transformations, and another solution which is training an equivariant reconstructor. And I'm going to delve in deeper into what do I mean by training an equivariant reconstructor. So we need to first define what is equivariance in the context of inverse problems. And this, for my surprise, was not very well defined yet in the literature. And what do we mean by equivariance in inverse problems? What we want is that a reconstructor is consistent for different transformations. Okay, so if I observe through a composition of A with a transformation, the transformation should go out in the reconstruction. This might look a bit confusing, but we can do sanity check. And if we think of famous estimators like the maximum a posteriori or the MMSE estimator, assuming a distribution is invariant, then we get this property. So F, if it's an MMSE or a map, it holds this property. Okay, and then we can go further and say, okay, if we don't have the map or the MMSE, but we are, for example, using a unit. So a unit, typically we will do some back projection into the image space, and then we will pass it through a unit. As long as the unit or whatever network is equivariant, then we will have an equivariant reconstructor. If we like unrolling, then we can also do the same. And as long as the denoiser step in my unrolling algorithm is equivariant, the reconstructor will be equivariant. Even going further, this is a trick that you can take whatever reconstruction algorithm and make it better at inference time by just averaging over transformations. So this is a trick called Reynolds averaging, and basically you say, I take whatever function and I average it over my group, and I get something that is equivariant. Okay, so all of these are equivariant reconstructors. And why this is useful? Because we'll see that if I choose one of these architectures, which I choose them by construction, by design, the loss will simplify. So we have the following simple theorem, which says that if F is an equivariant reconstruction by construction, then just minimizing splitting is the same as minimizing the equivariant splitting. Why? The expectation is gone over G. So we just need to split and that's it. And why the expectation is gone in an intuitive way is because it's inherent to my neural network. So if we use an equivariant architecture, we will learn in the null space. All right, so we trained our model with the equivariant splitting. We have this MMSE estimator if the conditions are verified. And what do we do at inference? So the naive thing we can do is just sample a single split given my operator and then reconstruct. Okay, but this is not the best use of my data because I could split it multiple times. And so a better idea is to just split and split and split all the times I want and average, and that will give me an even better. And if I want to go even further, I can analyze what is this, the structure of this multiple splitting strategy. And if I know this matrix QA1 and I can compute this expectation, the best I can do at inference time is this expression over here, which can be shown to be a convex combination of the MMSE estimators for the different splits, which is a good idea. Right? In practice, it's hard to compute this QA1 matrix, so what I recommend is just averaging over splits, which is really relatively easy to implement. So, what happens if we have noise? So far, I just focused on the null space and what happens if we have incomplete operators. But now let's add some noise to make it more difficult. So if we have noise, we can look at our splitting loss and see that actually we can divide it into two terms. One that is measuring consistency on the Y1, and another term that is measuring consistency on Y2 of my split measurements. So the problem of noise is not on the second term, it's on the first term. Why? Because the correlation between what we put inside the network and what we try to predict is only on Y1, right? Y2 and Y1 will have independent noises and there's no problem. So what we need to do is handle this first term. And for this, there's a very large literature on how to do self-supervised denoising losses. So here I'm just going to mention one method, which is the recorrupted to recorrupted method. I don't know how many have you heard about recorrupted to recorrupted? Raise your hand. None? Andrew. I'll have more explanations later on, but it's some kind of mathematical trick, a magical mathematical trick where you generate two independent vectors out of one by adding and subtracting synthetic noise. It sounds like it should not work, but it works. So you do this, and you get the first term that now approximates the clean first term, and the second one is always an approximation of the clean one. So this thing is also an estimator that is unbiased, and that will give you an MMSE estimator afterwards, okay, even if you have noise. The thing I'm assuming here is that you know the distribution of the noise, that you know that is Gaussian with a certain variance. Okay. So let's look some experiments. We did a bunch of experiments. Compressive sensing is just AIID random, image in painting, accelerated MRI, and also computed tomography. And we compared with another method we developed some years ago called equivariant imaging that is also using equivariance and is working with a single operator. So the first thing to check when you do self-supervised learning is how close are you to supervised learning. And we can do this by cheating and taking data sets that have supervised information. Of course, in real life, we would not be able to do this, but at least to check. We did this, and we see that, of course, we lose some performance with respect to supervised because we have strictly less information. But we are very close. We're always around 1 dB or on the ballpark of 1 dB below the supervised, even though we have seen no ground truth whatsoever. So to give you a visual example of how this works, so the measurements in in-painting are this thing. The neural network only sees this thing and never sees anything else, and can manage to reconstruct, so the one in the middle, very, very good details that are very close to supervised learning. All right. And so here is for in-painting, but the same is for MRI and CT. And in the paper, we have more figures. So if we want to compare with equivariant imaging, which is the main competitor here, we did some experiments for compressed sensing, changing the level of compression, so how many measurements we have per signal. And we observed that the new method was better at high compression, so at 90% of compression, just observing 10% of the pixels was still obtaining performances very close to supervised. So we can go very aggressive on the operator. And as well, how useful is using an equivariant architecture if we are not doing the Monte Carlo method. Using equivariant architecture is significantly boosting our performance. So it's good to use equivariant architectures here. So in the time I have left, I wanted to mention another application of this, which to me, so far I trained the models from random. So I initialized the weights at random, and the results were just from a random neural network. So this is good from an academic perspective, but from a practical perspective, maybe you can squeeze more performance by using a pre-trained model. And speaking about pre-trained models, I wanted to mention this recent other work we have done, which is called the Reconstruct Anything model, RAM, which is a foundation model for doing reconstruction, which we trained supervised across a very, very large set of tasks, so such as tomography, accelerated MRI, deblurring, demosaicing, and so on, multi-coil MRI. And so this model performs quite well on the training tasks, and maybe this is a conclusion that is a bit different to what I've seen in other talks. If you train supervise a model across tasks, it does generalize. But of course, if we go to a task or an image distribution that is very, very different, at some point it will fail. So we went for some real data, and we took some SPAD data, so the single photon avalanche diode data, which is supposed to have a Poisson distribution, but it doesn't in real life because the photon saturates and so on, and the distribution is complicated. And the other example is cryo-electron microscopy, which I've heard today, which has very high noise, and the noise is not exactly Gaussian, and so on. So in both cases, if we take a pre-trained foundation model, zero shot, it does a good job, but it's not great. Could be better. So here, the baseline is a CMOS camera, so it's not the same measurement. And here, the baseline is what you can do by some Gaussian filtering, which is what people using this data typically do. And when we fine-tune using the splitting loss, we get very good performance, and we manage to get rid of the artifacts that are left. And the thing that is very interesting here from a practical perspective is that once the model is trained, the fine-tuning can be done on very small data sets. So here, I just had nine SPAD images. So 9 SPAD noisy and incomplete images. And for the second one, I had 4K by 4K pixel cryo-electron microscope images. So relatively mid-sized data set. And these, once you are pre-training, it takes maybe in the order of minutes to do. So it's relatively cheap. So to conclude my talk, I spoke about how to do self-supervised learning with data coming from a single operator. And I showed you that the equivariant architectures actually are useful here and go beyond the typical usage of equivariance, which is just generalizing to unseen transformations. Here it's giving you information and discovering things in the data that you would not otherwise. We had seen that this comes with theoretical guarantees on what you learn. And finally, the kind of practical application of fine-tuning foundation models to really squeeze the best performance you can. And yeah, of course, the definition of equivariance in inverse problems. So if you're interested in self-supervised learning, we have a bunch of small advertising moments, but we have a long kind of review manuscripts that it's out on archive and out on Foundations on Trends in 1 week, where we did the work of trying to write everything in some common mathematical structure and explanations. And we also, if you don't like reading, you can check the YouTube videos. We did a tutorial, like a 3-hour tutorial on the topic. And so their code for this specific paper, it's online. And well, I will not speak about this because it's what Andrew is going to speak just afterwards. Thank you.